Welcome to clickmyproject.com. Let us discuss about the product title on OFDM receiver structure for a Subband-Selective mitigation of time variant interference. Let us discuss about the abstract. A proposal for an OFDM receiver structure with FPBB filter bank pulse blanking, which is adapted to the signal deformations induced by the signal blanking of FPBB. The reception of LDACS1 signals inferred by DME signals is taken. LDACS is an existing system. It causes interferences. So we are going for the FPBB. A receiver structure is proposed which consists of frequency selective pulse blanking unit, a blanking mitigation unit, and an iterative ICA cancellation unit. FPBB is used as a pulse blanking unit since it has most promising interference mitigation and overlapping frequency responses of the filter bank subband filters with suitable filter types to increase the time selective of the blanking process. Furthermore, we introduce an MMSC based soft blanking approach which makes use of a subband selective interference reduction scheme. In particular, we address the proposal for the deduction of the DME power in the subband to apply soft blanking. In addition, we show the methods to estimate the BAR values to each subcarriers according to SNR. These SNR values used to improve the channel estimation and channel decoding. Let us discuss about the flow diagram of the product. Here we have transmission and receiver section. First we discuss about the transmitter section. In transmitter section, first we take a source bit. The random values has been taken as input. Then the input values given to the encoder. Here we are using an convolutional encoding scheme. A convolutional code is a type of error correcting code generates parity symbols via sliding application of an Boolean polynomial function to a data stream. Then we encoded value converted into parallel streams. Then it is given to an modulation. Quadrature amplitude modulation 64 methodology is used for modulation. QAM is both analog and digital modulation scheme. It conveys to analog messages to digital bit streams by changing the amplitude of two carrier waves using the amplitude shift key in digital modulation scheme or amplitude modulation scheme. Then the modulated symbols has been given to a IDFT. Before that, we are inserting an pilot value. IDFT is inverse discrete Fourier transform. The discrete Fourier transform converts a finite sequence of the equally spaced samples of a function into an equal length of sequence equally spaced samples of the discrete time Fourier transform, which is complex value. The discrete Fourier transform provides an discrete samples of 1 cycles. If an original signal is 1 cycle of a periodic function, the discrete Fourier transform provides all non-zero values of the 1 DTFT cycle. Then adding a cyclic prefix. Cyclic prefix refers to the prefixing of symbols with a repetition of end. Although the receiver is typically configured to discard the cyclic prefix samples, the cyclic prefix serves two purposes: as a guard interval, as a repetition of end of symbols. Then the D2A converter, digital to analog converter. A digital to analog converter is converting the digital signals into analog signals. A transmitter filter is used to form the continuous signal. Then A to D Then ECB is equivalent complex baseband to RF and RF to ECB. Then it is given to a low pass filter. Then we have performing A to D converter. I to D performs the reverse operation of function. Receiver side we have reverse function of the transmitter side. Then removing the cyclic prefix. Then perform DFT. Then demodulation. QAM demodulation. Then we perform decoder. A decoder is a better be decoding algorithm we are using. Then the output. By the output function, we are analyzing the performance of the process. Let us discuss about the running procedure of the product. For executing the product, run the main file. By running the main file, many output forms. These are all related to our flow diagram. Now we see the outputs. This is input data, encoded data, IDFT data, DFT data, demodulated data, and at last this is decoded data. Now we discuss about the performance of the process. This is the different sampling rate and subband filters bandwidth for FPBB. This is fs equal to 1250. Both are fs equal to 1250 kilohertz. In case 1, fp equal to 78 kilohertz. The start point is fp equal to 70 kilohertz and fp equal to 150 kilohertz in case 2. This is fs equal to 1250 kilohertz and fp equal to 78 kilohertz without approximations. Then MMSC based pulse blanking. No DMA is our proposed system. These are all our existing system. This is no DMA line and channel estimation for FPB. This is the no DMA proposed system. Our proposed system is filter blanking, pulse blanking. By using filter blanking, pulse blanking, we can get the low interference. This is our proposed system. Thank you for listening.